Good morning. I'm going to continue the discussion of thermodynamics, including ideal gases. And we're going to talk today about the adiabatic process and other things. First of all, let's deal with an error. Sometimes I make an error. You can find them. I do the derivations live, so I don't carry notes. Errors can happen. This is a typo. I divided 1,000 instead of 4186. 4186 joules per kilogram per degree centigrade is the specific heat of water. For some dumb reason I put in 1,000, knowing that the molar specific heat is going to be 75 compared to 4186 for kilograms. This is for moles. Just go back and change your notes, get rid of the 1,000 and put in 4186. That's in the last lecture. Now, where are we heading? We're doing in the adiabatic process. Remember, in the isothermic process, we derived that W is nRT log V1 over V2. Temperature is a constant, but the volume changes. Now we're going to do the adiabatic process. What's the adiabatic process? The adiabatic process says delta Q equals 0, no heat enters or leaves the system. The system is totally insulated. The volume can change, the pressure can change, the temperature can change, but no heat goes in or out of the system. Keep those parameters in there. Alright, so what else? Then we're going to head on to what is meant by reversibility. But I'm just going to state it because that's one of the things that needs to be covered in detail. The texts and articles do not properly deal with the idea of reversibility. Even Fermi, I'm not happy with his discussion. I want to get it just right. That's what I do with these lectures. I make sure I leave no stone unturned. And that will lead up to the second law of thermodynamics. Second law of thermodynamics, I'm going to give a very quick, my phrase, actually due to a colleague, my phrase definition of it. Okay? This is heading into information theory, by the way. We might do a little class on that as well. Entropy and so on and so forth. Engines are coming up. What are they? They're thermodynamic engines and they're devices for extracting mechanical work from heat, a heat process. Okay? So that's where we're heading, and there's a lot of interesting stuff coming up. Just right now, for this few minutes, we're going to look at the adiabatic process. Remember, we had isothermic, that's constant temperature process. Isobaric, constant pressure process. Isochoric, constant volume process. And now adiabatic, delta T equals 0. That means that when we have a configuration with internal energy only depends on the temperature, then close by to it, by an increment of delta U, this guy changes to slightly different configuration, but this delta U is just a variation. Okay, so that's what we're doing, the adiabatic process. Let's just remind ourselves don't forget that CV is 2/3 R. Now I didn't put that delta T in there, right? So I should say delta T is what we have there, okay? And we also have PV right? We have the ideal gas law, rewriting it this way. What do we need to put down? Anything else? Okay, so first law of thermodynamics says that this delta U is delta Q minus P delta V. But we're dealing with an adiabatic process. No heat enters or leaves the system, adiabatic. All right, so therefore, what do we have? We have delta U equals P delta V, and delta U is this guy here. P delta V. But P is nRT over V. Okay? Now I don't need this N here. Now I'll divide both sides by T. Now we'll leave the V over there. So therefore now we can integrate delta T over, listen. We integrate delta x or dx over x, or delta x over x, we can make it a differential. We get log x plus a constant. So we integrate both sides of the equation and we get log t. Actually, I'll bring the equal sign and make it a 0 like that. So we get log t plus r over c log v equals a constant which we'll call lambda 1. Now we'll combine these two. When we add logs, it's the same as multiplying the quantities. Now, when we multiply a logarithm, it's the same as an exponent over the quantity. Okay? So this is really log v. Actually, let's just write it all out. Let's call this lambda 2, even though it's the same constant. Now we'll combine them. So far, so good. Log of this guy here is this. So now I can say, take the log of this. It's going to be the log of another constant. Well, the log of a constant is just another constant. We call that next constant log 4. Now remember, R is Cp minus Cv, okay? So look at this guy down here. Now I've dropped it here. No, I haven't. It's here. R over Cv. And that's lambda 4. So we continue on now with our trek. Cp over Cv is gamma. Cv over Cv is 1. I keep changing the constant, it doesn't matter, you can call it what you want, it's still lambda 4, but now we have the expression Tv to the power of gamma minus 1 is a constant. And we'll say that's adiabatic number 1. So Tv to the power of gamma minus 1 equals a constant. T we can rewrite using the ideal gas law as PV over NR, so we'll put that in for here. Times V. I'll just make up some new constants, lambda 6. So here we have a P. Now V times V to the power of minus 1 is the same as add the exponents, and one of the ones goes away, this one and this one, and we get V to the power of gamma. Now this guy here is P, and we have V to the power of gamma. I'll bring the NR over here. Now N is going to be a constant, R is a constant. N is a constant for the case of a fixed mass of gas, which is what we always consider. So now we have a new equation. Which we'll call adiabatic 2. Adiabatic 2 says that the product PV to the power of gamma is a constant. These are conserved quantities, if you like, within an adiabatic process. What's a conserved quantity? Something that doesn't change. Where did we have that before? PV over T is always a constant in the ideal gas law, and that means that this P1 P1V1 over T1 for some configuration 1, 2, 1, 1, 1, 1 of volumes, pressures and temperatures. If we rearrange the situation but we don't change the N, we keep a fixed mass of gas, then we can say P1V1 over T1 is P2V2 over T2. So these are the two results that I want to derive for the adiabatic case. Let's leave it for that, and in the next class I will come along to dealing with the second law of thermodynamics, which is quite interesting. I'm going to state it right now. Here is the second law of thermodynamics. There exists yet another state variable other than volume, pressure and temperature, and we're going to call it S. Okay, that's coming up. We'll deal with heat engines though before we actually get to that. What is a heat engine? A heat engine is a device for extracting mechanical work from a heat reservoir, okay, or from a heating system. Convert delta Q into delta W. That's what an engine does. James Watt, Clausius, all the people who were studying Thermodynamics, when the Industrial Revolution came about, this was a big part of it. And it's quite interesting, and it leads into being a branch of physics in the end. And it leads nowadays, from about 1949 on, a guy called Shannon, you know, the idea of information is related to it. That's not fully understood. There's another guy called Boltzmann that we've been using as constants all along. He has a little equation written on his tombstone. Yeah? Boltzmann's law. It's very short, but it's one of the most profound equations in all of physics. Also, so far I have not come up with the following. Now sometimes I make a mistake, and that's the way it is in a live class, a live lecture, where we have no notes, and we're not sure where we're going. Well, we kind of have a rough idea of what the map is. I have an injury. I'm not recovered from it yet, so I'm moving slowly. Now, we got gamma mu rho sigma in the covariant derivative for people who are studying a little bit more advanced physics in general relativity. Now, I never derived an explicit expression for that explicit expression, because all the ways I've seen it done are very unsatisfactory and too long. And then some people don't really derive it. They derive an expression for what's called the geodesic equation and say, that's in there, here it is. It's not good enough. You have to be able to derive it, otherwise it's no good for a student. The expression that it is I'm getting this right? I'm not. That's what the expression for the Christoffel symbol looks like, but I want to be able to get that derived just using algebra in an elementary way. Elementary doesn't mean simple. It could be that the derivation will be very long. Actually, there is a trick to derive it, which involves a lot of algebra. You take derivatives and you add and subtract two terms, out it falls. I'm not happy with that one either. So we'll see. As soon as I get one sorted out, you get it. Now the other one is this. What is a reversible process? That's coming up. So far the definitions I've seen and the explanations of that are not really good. So I have to sit down and have a couple of glasses of sake and think it through. That's where most of your lectures came about, by the way. I just thought stuff through and made it as simple as possible. Okay, so that's what's coming up, and here's our two good results for today. And in the adiabatic case, these two equations are valid in conjunction with delta Q equals 0. All right? We'll stop there.